NG11U. At dinner time.
Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Good, good. Yeah, tired probably. It's we're getting right up close to spring break now, so we have one more week after this, and then we can take a break for a week, right? Okay, so today we're going to finish up our lecture notes on time marching schemes, and so after the lecture today, we'll basically look at two examples of how to implement two more examples on how to implement finite element codes with time marching. And so that should definitely help you out with homework 4. And so remember, homework 4 is going to be due next Friday. That's going to be basically the very last day before spring break. Okay. And it covers just all time marching problems. And so I think the format for homework 4, I think is the same as the last one. And so the first part, the first worked out part, we're going to do basically, calculations by hand and derivations by hand. And then for the third problem, I'm having you implement Matlab code, and I provide you starter code for that as well. Yeah. Exhausted, yeah. I'm tired too. It's definitely that time of the semester where it really starts to be a grind. But we're almost at spring break, so just hang in there for one more week. All right, and so other announcement I want to make is I graded your midterms on I think it was last night. Yeah, I finished grading last night. And so the average was good. So you guys did really well. So the average, I know what it says on Canvas, but when I computed it by hand, the average was a little bit lower than what they have on Canvas. I'm not sure how they compute that thing on Canvas. And so the average was about 42 out of 50, just a little bit over that. So you guys did really well, and so that's really good. And so if this kind of keeps up, I think probably I won't end up having to scale the class, which is typically what happens with my tech electives. So for my electives, the scores tend to be a bit higher, and that's just because it's kind of a more specialized topic. Yeah, you guys did really good. So I was really happy with that. There's no PDF with questions for homework 4. Oh, did I not post it? Let me see. Homework 4. It should be there. it should be there. Let me see. Did I not put it in the? Oh, I forgot to link it. I forgot to link it to the assignment. So actually, let me go ahead and do that right now, really quick. Right. But you can find the PDF for the assignment in the files page. But let me go ahead and link it here. I just forgot to put that in. Yeah. Okay. And so as of right now, the homework PDF should be there. So you should see the list of questions now. Yeah. And I've also posted 2 videos. If you look on the assignment page on Canvas, you'll see that I posted 2 videos alongside it to give you an idea of what the solution should look like for problem 3. Okay, and so today, what I was working on before the class, I was working on your guys' final project, and so I'm not quite ready to give you the spec checks. I'm still kind of playing around with the numbers, but I'm almost there, and so I can kind of show you what I have in mind for that. But before I start, I'll describe it in a second. But before I start, are there any questions on the midterm or anything else that I can answer before we get started? Okay. All right, so let me just show you really quick what the final project is. This is probably not going to be the final one because I'm still kind of playing around with the numbers, but just to kind of give you an idea. But basically, what I want you guys to do for the final project is I'm having you simulate a gas leak, okay? And so basically what's going to happen is that you're going to have a square room like this, and then in the middle of this room, there's going to be gas that's leaking out, okay? And then over time, the gas is going to start to fill the room. But eventually what you're going to do is I'm going to have you open up a window on the right side and on the bottom. Right, so actually, let me go ahead and play that again. Okay. And then when the window's open on here and on the bottom, of course, that's going to let the gas out of the room. Okay. And so this is kind of a situation that, if you work for like the gas utility company, this is a situation that they want to avoid most of the time because, they're very diligent about checking for gas leaks. Because if you breathe in natural gas or anything like that, obviously it's toxic to humans, and there's also all the fire risks as well. And so I was hoping that this project right here would be something that might be relevant for some of you who are going into those into that industry. Yeah. You can interpret it as farts too, so that's another interpretation. But it would be it would be someone that's probably farting straight for like 5 seconds, because we're going to be simulating it for about that long. So I thought a natural gas leak or a utility or a gas line break is a little bit more realistic to what we're going to do for this problem. Yeah. So I'm still playing around with the numbers. So I'm still playing around with the numbers a little bit, and so I want to kind of make it look a little bit nicer. So I'll probably have it ready for you guys by Monday. Yeah. Actually, yeah, Alex. So that's actually I remember our conversation at the beginning of the semester. That's what kind of inspired me for this project, and so that was definitely a big part of it. So let me play around with it a little more. I'm still writing the specs as you can kind of see from here, and then we can talk about it in detail on Monday. Okay. But for now, let's go ahead and continue back on with time marching schemes. And so actually, I was kind of thinking about, last year. So I taught this, I taught this class a year ago in the spring of last year. And this was about the time that, COVID started to hit and we had to go all virtual, which is kind of a shame, because these lecture notes on time marching schemes, I'd say these are probably the most important ones for the project. And so what ended up happening was that everyone was kind of lost on the final project last year, because this is when things, this is when I was first testing out virtual teaching. We were testing out things with Zoom, trying to find the best mode for that, and also people had to move home and get things settled. So people ended up being kind of screwed for the final project last year, just because these lecture notes in particular with time marching schemes kind of got lost in translation with all this stuff. So what I'm hoping for is that this year we do a much better job of going over these time marching schemes, and we go over kind of the sample codes that I left you guys, so you'll be in a much better shape for the final project. Okay? All right, and so let's go ahead and continue on. And the subject is going to be time marching schemes. And in particular, what we're looking at are situations where either the boundary conditions or the properties change with time. Okay, and I believe exactly where we left off was with an example, right? And so let's start with just a 1D example. So let's start with something simple. And so we have our equation looks like this. And so we just have an unsteady diffusion equation. So we have d phi dt is equal to 3 d squared phi dx squared. Okay. And our boundary conditions, one of them is going to change with time. And so the first boundary condition, which is going to be on the left side of the domain for our 1D case. Okay. And so this is going to be the boundary condition at x is equal to 0, and it's going to change with time. It's going to be cosine of pi t. Okay. So it's basically going to go up and down with cosine. And then the second boundary condition is just going to be a constant. And so we have d phi dt, or d phi dx, I'm sorry, at x is equal to 1, t. This is equal to 2. Okay. And our initial condition, we'll start with the 0 initial condition, just kind of simplest thing we can do, right? And so we have phi at all values of x, and t is equal to 0 is equal to 0. Okay. So initially we're going to start with a a 0 initial condition. And for this problem, we're going to march this system forward in time with implicit Euler and a time step size of 0.1. And so remember, time step size refers to delta t. Okay, so we're going to have delta t is equal to 0.1. Okay, and we're going to use a spatial grid of 5 points. Okay, and so remember, since we're in 1D, because we don't have any derivatives in y here, and so we only just have a 1D domain like this. Okay. And so we can number our nodes just like that. And then we'll assume that the spacing in between each of these, which is going to be delta x, we'll assume it's 0.25. And so the overall length of our domain is just 1. Okay. All right. And so I picked this example because we actually did this example in the previous set of time marching scheme lecture notes. Okay. And so I'm going to skip, the whole plugging into implicit Euler and all that stuff, because the only thing I really want to focus on here is this new boundary condition, which changes it with time. Okay. But in terms of all the interior nodes, we're going to use the same equation for that. And so if you remember from last time, after we apply implicit Euler, we ended up with the following equation, right? So we have minus 4.8 times phi at I minus 1 and plus 1 plus 10.6 phi I and plus 1 minus 4.8 phi I plus 1 and plus 1 is equal to phi I at n. Okay. Right. And so remember, for all time marching schemes, we put all of the terms with n plus 1 on the left side of the equal sign and all the terms with n on the right side. Right? And the fact that we have a lot of n plus 1 terms on the left, as opposed to just one, this tells us that we're in an implicit Euler solution. Right? Because if this was explicit Euler, then we'd have much more terms on the right-hand side, and we'd have just one, n plus 1. But the fact that we have three terms on the left side with phi n plus 1, this tells us we're on an implicit scheme. Okay. And so what we can do is we can apply this to all of the interior nodes in our system, and also apply our boundary conditions. Okay. And then we're going to end up with a system of 5 equations that we're going to march forward in time. All right, any questions on this? Okay, so let's go ahead and write out our 5 equations. Okay. And so we're going to have equations for each of the values of I. Okay. And so first we have I is equal to 1. And for I is equal to 1, this is our boundary condition on the left-hand side, right? Because this is our very first node. And so we have phi 1 at n plus 1. This is going to be equal to our Dirichlet boundary condition, which is our new one right here. And so it's going to be, cosine of pi t, okay? And we'll say that this is equal to cosine of pi t n. And so this is new. And so this is, I think, the first time that we've seen t enter into our system of equations. And so, in terms of writing the equations, it's fairly simple, but I think the important thing is seeing how it's implemented in the code. Right? All right, so next we have I is equal to 2. And so if I is equal to 2, we have minus 4.8 phi 1 n plus 1 plus 10.6 phi 2 n plus 1 minus 4.8 phi 3 n plus 1. Okay, and this is equal to phi 2 at n. Okay. And then since node number 3 and node number 4 here are also interior nodes, we're going to have, very similar expressions for these as well. Okay. And so I'm going to skip writing it down just so that we can get to the MATLAB code. Okay. But I'll say that these are similar to I is equal to 2. The only difference is that, everything is shifted up by 1 because our I is going up by 1. Okay. Right. And then finally, we have I is equal to 5, and this is our Neumann boundary condition. And our Neumann boundary condition is given by this expression right here. So we have phi5 at n plus 1 minus phi4 n plus 1. And this is going to be equal to 2 delta x, which is equal to 0.5. Okay. All right, and so putting this in matrix form, we get the following. Right? And so first we have our coefficient matrix on the left. And so our coefficient matrix looks like this. Okay, so that's the first row. That's the second row. Third row. And that's the fourth row. And then our last row looks like this. Okay. Okay. Then we have all of our phi terms. These are evaluated at n plus 1. Okay. And on the right-hand side, we have the following. And so for the first node, since we have something that changes with time, we have cosine of pi tn. Okay. And I use t sub n here to denote the fact that, we're going to use the current time for this. And then the rest of the entries just kind of fill in just like that. Okay. All right. And so what we'll see in the, what we'll see next is you'll see my MATLAB implementation of this, which I posted onto Canvas for you to look at as well. And so this is kind of just a worked out example. And so there's nothing for you to fill in yourself. And so, if you want to follow along with your own MATLAB, you can download the code and run it, or you can just kind of just watch me run it. And it's kind of the same thing. Okay. All right. Any questions on this before we move to the map? We look to the Matlab script. Okay, so let's go ahead and look at the Matlab script and see what we got. Okay, and so this this code right here is, I think it's called time stepping example implicit sinusoid. Okay, just and it's named that because we have a sinusoidal boundary condition. Okay. All right, and so the first thing we have to do is we have to define our left-hand side matrix. And so that's what I'm doing here. And so this A matrix is basically going to be the same as this matrix, right here. And so you can kind of, look at entry by entry and you can see that it's the same. Okay. Right. And so the next thing that we're going to do, actually, you can ignore this part because we're going to, we're going to set this. Okay. And so the next thing we have to do is we have to define our variables for the next solution and the current one. And so this sol next, remember, this is phi at n plus 1, okay? Because that's the next solution that we want to solve for. And so remember, sol next is always this guy right here, okay? And then sol cur, this is phi at time step n, okay? Remember, the difference between these guys is that sol next, remember, this guy is unknown, and we want to solve for it. Okay. Whereas phi at n, this is known from the previous time step. Okay. Right, so that's why you see, the phi n's here on the right side of the equation. Okay. All right, and so here's a little bit of a bookkeeping lines of code here. So this is basically going to enable us to write out a video. Okay. And then here we're going to define our time parameters. Right. And so this is new. And so this line in particular right here, t is equal to 0, is new because what this variable is going to do, this variable will keep track of the current time. as we march forward. Okay? Because if you look at our system of equations here on the left, we need to be able to plug in t somehow, and so we need to basically keep a variable, that stores t, and we're going to start this t variable at 0 because that's kind of the convention, is to start these time marching solutions with t is equal to 0. Okay, and so now that we've defined all of the parameters and all of the variables, let's go ahead and go into the time marching loop now. Okay, and so for the time marching loop, we're going to loop over this variable to t step, and we're going to go from 1 all the way up to nt, which is the number of time steps, right? And so for this problem, I'm just simulated for 100 time steps just so that we get a decent video, right? And then what you'll see is that, in every time step, these this forcing vector here is going to change. Okay. So in each time step, the forcing vector will change. Okay. And it'll change for two reasons. And so the first reason it'll change is that we have cosine of pi t here. And so every time step, t is going to be a different value because we're simulating it at different values of t. And so every time step we're going to have to recompute cosine of pi t, right? And so that's exactly what you have here. And so we have b at 1 is equal to cosine of pi t, okay? And so that sets the first entry of this right-hand side vector equal to cosine of pi t. And then from there we're setting each of these entries in the forcing vector, which are phi at the previous time step, right? And so that's why you see b at 2 is equal to sol cur at 2, b of 3 is equal to sol cur at 3, and b of 4 is equal to sol cur at 4, okay? All right. And then, so now that we've defined this and we have our coefficient matrix, our coefficient matrix actually isn't changing with time here. And so, we don't have to recompute it. And so just like every implicit Euler solution, you're going to do a linear system solve, right? And so in order to solve for this, basically we have to invert this matrix here and multiply it by this one. And so that will give us our phi at n plus 1, okay? Right, and so that's what this line of code does. We have sol next is equal to a backslash b. And then once we've solved for sol next, then we can set that equal to current solution. And so remember, whenever we do time marching, we have to update the current solution. Okay. Okay. And so now that we've we've assigned our right-hand side vector, we've go ahead and solve for phi next, and we've updated our solution. These lines of code here are just for plotting, and so don't worry about these too much. And so I usually provide those for you. Okay. And the last line of code that we'll go over before I run this is this guy at the very end. Okay? So it's a very innocent looking line of code, but it's extremely important for problems that depend on t. Okay. And so because we have this cosine of pi t here, we have to update the time variable on each time loop. Okay. Okay. And we talked about this last time too. And so in order to update the time variable, we just do t is equal to t plus dt. Okay. And so all we're doing is basically saying that the new value of t is going to be equal to the old value plus the time step size. Right? And so we're using our usual kind of update notation for the time here. Right? Okay. And so this is really important because you need to have this. Otherwise, your t variable is just going to be stuck at 0 the entire time. All right. Any questions on this before we start running the solution? Let's see. Okay. All right. So let's go ahead and run this guy and let's look at the results. Okay. Is there a video that we were supposed to download with this? No, I didn't post the video, but if you run the code, it'll produce the video for you. So it's a very lightweight code, and so that's why I didn't post the video. And so the video looks just like this. Okay. So remember, this is our vibrating string. My laptop is kind of spazzing out right now because I think I was running the project a little bit too many times. But you can see the string basically vibrates up and down. Okay, because remember our left-hand side boundary condition here is changing with time. Okay. All right, question. So would it be possible to show what the code would look like if we were to use a while loop rather than a for loop? Sure. Yeah, I can do that real quick. And so a while loop, for a while loop, remember a while loop will basically iterate until the condition is met. And so I think the way that I would do that, I would say that t step. Let me initialize this to 0, right? And then while I would do while t step is less than n underscore t, right? And then inside here, I can basically do all the same things. Okay. But the last thing I would have to do here is that I would have to update my t step variable. Okay. Because right now what this for loop is doing is basically iterating, n sub t times, right? And so where n sub t is 100. And so we have to basically make it so that this while loop will also iterate 100 times, right? And so one way that we can do is we can kind of forcibly put in the counter variable here. And so we can say that, if t step starts at 0, then every loop here we can say t step is equal to t step plus 1. So let me go ahead and comment all this out. Okay. And this should do the same thing. And so fingers crossed, let's go ahead and run it. Okay. And so it still does the same thing, computer lag and all. I think I need to restart my computer because I think I forcibly stopped the project code a little bit too many times. But that's how you would implement it with the while loop. And so with the while loop, you have to kind of manually keep your counter variable here, and then and then go make sure you update it from that. Yeah, my laptop is tired too. I guess we're all tired at this point. Yeah. All right, and so the most important part of this example here. So comparing this to the implicit Euler code that we went over last week, the big differences here is that now we have one of these variables, or one of the entries in our matrix here changing with time, and in order to make that work, we have to make sure our time variable here is also updated, each time step. Okay. And so, we're going to use this t variable quite a bit. And in your projects, you're going to need to use a t variable a lot too, because your project, obviously, things are going to be changing with time as well. Okay. All right. Any questions on this before we move on to the next example? Okay. All right. And so that's basically a 1D example. And so the 1D example, did I try downloading more RAM? No, I did not. I'd rather buy more RAM. And so that was, that first example that we just did, first of all, it was 1D. And so, that's relatively simple there. But it was also an example of how the boundary conditions can change with time, right? And so, there was nothing in this equation here that actually changed with time. It was only just the boundary conditions. But we're not limited to those situations. And so we can actually look at situations where the actual parameters within the problem actually change with time. And so, the most common way that this is implemented is for convection velocities that change with time. Okay. And so we're going to work on this example next. And so in this example, what we're going to see is what happens when u and v change with time. And you'll see an implementation in 2D as well. Okay. All right, so let me stop sharing here. Let me come back to my iPad just so we can write out the equations. Okay. And this will be nice too, because I think this will be, the first time that we see an implementation in 2D of implicit Euler. And so this is actually going to be one of the closest things to your project, because for your project, it's going to be a 2D problem, and I'm asking you to do it with implicit Euler, just because I was trying it with explicit Euler, it just wasn't working out that well. Okay, and so this is the next example. And so in this example, we're going to have an unsteady convection velocities. All right, and so the full equation for this is we're going to have d phi dt plus u, but u in this case is going to be 50 cosine of pi t, okay, d phi dx plus sine of pi t d phi dy. Okay. This is equal to 3 d squared phi dx squared plus d squared phi dy squared. And then we're going to have no source. Okay. And so from this equation, what you can see is that our convection velocities are now changing with time, right? And so we have u is equal to 50 cosine of pi t. Okay. And v is going to be sine of pi t. All right. And so, once again, what you'll see is that in the time marching loop, we're going to have a t variable that we need to maintain, and we're going to use that t variable for for the solution. Okay. All right. And so let's put some more parameters on this. So let's use a time step size of 0.1, and then a number of time steps. We'll do this for 500. Okay. And then what we're going to do is we're going to advance the system forward with implicit Euler. Right. And so we haven't seen a fully worked out example in 2D with implicit Euler. And so, this example will be kind of serving as that example for you. Okay. And then the domain that we're going to be solving on looks like the following. Okay, so we have phi is equal to 50. Phi is equal to 50. Phi is equal to 25. Phi is equal to 25, right? And so those are all our boundary conditions. And we're going to have 30 nodes in each direction. Okay, so we have nx is equal to 30 and y is equal to 30. Okay. Okay. Any questions on this? Okay. And so what we're going to do is since we're implementing this with implicit Euler, let me write out the generic, implicit Euler formula that we went over, I think, maybe a couple lectures ago. Okay. Right. So 2D implicit. I'm going to do it just in generic terms for now, because remember, a lot of these will just end up being just directly implemented into our code. All right, and so we have minus u delta t divided by q delta x. Okay. And of course, this is assuming that we use central difference for each of the convection terms. And so we'll assume that our grid sizing is going to be small enough to have a stable solution. Okay. And then we're going to have k delta t minus k delta t over delta x squared. This is multiplied by phi I minus 1, comma j at n plus 1, okay, plus u delta t divided by 2 delta x minus k delta t over delta x squared, phi I plus 1, comma j n plus 1, okay, plus minus v delta t times 2 delta y minus k delta t over delta y squared times our bottom neighbor n plus 1, okay, plus v delta t over 2 delta y minus k delta t over delta y squared, phi I j plus 1 to the n plus 1, okay, plus 1 plus 2k delta t over delta x squared plus 2k delta t over delta y squared times phi ij n plus 1 is equal to phi I comma j at n, and then plus a source term, but in this case we have no source, right? But I'm just going to put it in just for now. All right, and so it's a doozy, you know, it's there's a lot of terms to keep track here, but remember, you know, a lot of these are just going to end up just being you know, directly inputted into the code. Okay. Okay. And so in the end, you know, once we implement all of these coefficients, you know, we're going to end up with a system that looks like this, right? And so we're going to have A, where A is our left-hand side coefficient matrix, right? So just like the same as we had for the 1D, okay, multiplied by the vector of phi at n plus 1, right? Right? And so this is going to be equal to phi at I comma j at n plus q at I j. Okay. Right. And so in our code, you know, we're going to, you know, compute these coefficients. Okay. But the difference here, remember in this problem, you know, in this problem we have convection velocities that change with time. Right. And so we have these u's, these v's. Okay. All of these change. And since they change with time, what we're going to say is these change every time step. Okay. All right. And so since these guys are changing every time step, what that means is that this A matrix, or this coefficient matrix that we compute, this has to be recomputed at each time step. And so this is significantly different than, you know, all the other problems that we've seen before, because, you know, if you look at kind of the last code that we did, you know, we kind of did like we kind of preloaded our you know, our A matrix, and so we kind of filled those in first before we enter the time stepping loop, right? And so in this code, what you're going to see is that the time stepping loop is going to come first, and then inside that time stepping loop, we're going to redefine, you know, our matrix A, right? And so what you'll see is we'll have a loop within a loop within a loop. And so we'll have a triple nested for loop. Okay. And so these, you know, these simulations, you know, 2D simulations with, you know, with time varying boundary conditions, these aren't cheap. And so, you know, I was running the project code over and over again earlier, and each run of the code took about 90 seconds. And that was with kind of a fairly modest mesh too. So that was only about 50 by 50. And so, you know, for these problems, like, you know, you can't just keep running it willy-nilly. Like, you really kind of need to, you know, make sure that your you know, your coefficients are good. Otherwise, you're going to be running this, you know, you're going to be waiting like a minute, 2 minutes for every run, and it's not going to be a pleasant experience. Yes, it's you know, it's going to be tough. And so you really want to make sure that, you know, you double, triple check your code before you run these guys, because a lot of times you can't afford to be running it, you know, hundreds of times to help you debug. Okay. Any questions on this before we look into the code and see what it looks like? But did I try implementing in Python though? I did not. And so I'll leave that up to you to see if that's it. Python should perform a little bit better, but you know, the reality is, you know, you have a loop within a loop within a loop. And so no matter what language you're in, that's always going to be pretty expensive. Yeah, Python should do a little bit better. I'm not sure how to make videos in Python though. So I'll you know, you know, we'd have to look up. Okay, and so let me go ahead and share my screen again. All right. So let me go here. Don't care about recent Canvas notifications, right? And then here is the second code. So this is the other code that I posted onto Canvas. Ignore these notes that say titanium. So, obviously I wrote this last year. So titanium, actually after this semester is not going to exist anymore. And so, this should say canvas. Okay. All right. And so this is the code that I posted, which will run our solution. So actually, let me run it first, just so you can kind of see what the solution looks like, and to kind of give you a sense for how long these solutions take. So actually, this one's not that bad. But you can see, we have this oscillating flow where like this membrane is kind of going down, then up, then down, as my computer kind of croaks through this this simulation. It looks smoother. It looks smoother in the video, right? But that's kind of what we're aiming for here. And so we have this membrane kind of changing with time. So let's see if we have the video here. And so that's what it kind of looks like in real time when your computer is doing a little bit better than it is for me right now. All right, so let's look into the code and see how we actually implemented this. And then let me keep this on here just so that we can see. Okay. All right, and so the first section of the code is exactly the same as we've done before. And so we're just defining all of our variable parameters here. Okay. And so of note, we have our diffusion coefficient, and so this is 3. Okay. So remember, I'm doing the weird viscosity as diffusion thing, okay? And then we're defining our left-hand side matrix and right-hand side vector, okay? And just like we always do with time marching schemes, we have to define a variable for the current solution. So this is the solution at time n, and this is going to be the solution at time n plus 1, okay? And then once again, this is MATLAB specific code to make a video. And so I'll write all these codes for you, so you don't have to figure out how to write a video. You kind of just have to fill in kind of the codes in between. Okay. All right. And so from here we enter the time stepping loop. And so this is a lot earlier than what we usually do, right? Because remember, for this code, since we have these velocities changing with time, we have to update this A matrix every single time step, right? And so the reason we have this is, since we have to update the left-hand side matrix A in every time step, we will compute A inside the time stepping loop. Okay. All right, and that's what you kind of see right here. Okay. All right, and so first thing, we're looping over time, and you can see even before we start to mess with A, we've computed the velocities, right? And so since our velocities are changing with time, let's go ahead and just compute these right away. And so we know that our x velocity is equal to 50 times cosine pi t, according to what's in the problem spec right here. And then our y velocity is going to be sine of pi times t. And so that's what we have right here. Okay. And so remember, this t variable is something that we're going to maintain ourselves. And so at the bottom here, you can see that we're going to update time. And so we can go ahead and use that in our solution here. Okay, and so from here, here is our usual nested for loop for, setting our left-hand side, matrix, okay? And so now this is inside the time stepping loop. Remember, this is changing every time step. But, besides the fact that we've moved this, it should look very familiar to you guys, right? And so just like we always do, we have a nested for loop that loops over all of the interior nodes, right? And so that's why we go from I is equal to 2 to nx minus 1. And then j is equal to 2 to ny minus 1, right? And then just like we usually do, we have our ID numbers. And so, we have to compute the ID numbers for I comma j, and also for all of the neighbors, okay? And then from here, we can start to input the coefficients into the A matrix, okay? And so you can see that these, all of these equations here are basically direct transcriptions of what we have for here, right? And so let's look at the left neighbor first, since I've already kind of have it highlighted, right? And so the coefficient for the row my ID, but for the left neighbor, this is equal to minus u times dt divided by 2 dx minus our diffusion coefficient times dt divided by dx squared, right? And so this formula right here for the left neighbor corresponds to this formula over here, which is in front of phi I minus 1 comma j. Right? Okay. And we're going to do the exact same thing for all the other coefficients for each of the other neighbors, right? And so next we have the right neighbor. And so the right neighbor is this guy. And so you can see that's going to match up with this line of code right here, right? And so a at my ID comma right ID, this is u times dt divided by 2 dx minus k dt minus divided by dx squared, right? And then same thing for the, I guess next we have the bottom ID. And so bottom ID is going to be this one right here, okay? We'll actually have this backwards. And so it should be, oh, I never caught this before. And so actually this one should be positive, and then this one should be negative, right? Right? Because we have the bottom, the bottom neighbor here is a minus v times dt, right? And so that's why we have a minus out here for the y velocity. And then we have a minus k dt of dx dy squared. Okay? And then for the top neighbor, we have a positive v dt divided by 2 dx dy minus diffusion coefficient times dt divided by dy squared. Right? And so there's a minor typo in the code that I uploaded. And so, you know, if you want to go ahead and fix that, you can. Okay. But I think it should still produce, you know, a good solution for us. And then finally, we have the coefficient for my ID, which of course is the coefficient for phi I comma j. And we have, you know, this exact thing right here. So we have 1 plus 2 times k dt divided by dx squared plus 2 times k dt divided by dy squared. Okay. And in this particular case, let me cancel out the source term just so that we don't have to worry about it. But if you need to implement a source term, you can do that here as well. Okay. And then what you'll also see is that in the right-hand side vector for b, I'm also including the solution at the current ID. And so this Solker my ID is going to be the exact same thing as this guy right here. Okay. Right. And so remember, you know, for these codes, you know, I know that, you know, these expressions here are pretty long and intimidating, but just take it step by step and just take it kind of neighbor by neighbor and just transcribe just whatever equation that you have here directly into the code, you know, and you'll be just fine. All right, any questions on this? Okay. And so, you know, I know I'm kind of going through it pretty quickly right now, but definitely, you know, take the time, you know, when you're working on the homeworks and look at these sample codes and look and see how I've implemented it and cross-reference with the notes, right? And so, you know, if you could kind of set up, you know, if you have dual screens, that's great. You can set it up on dual screens, but, you know, if you have just one monitor, you can just set it up kind of in dual, in dual kind of view like this. Because, you know, honestly, you know, a lot of your homeworks, a lot of the homework problems that I give you, you know, you can complete a lot of the MATLAB parts just by taking the code that I've shown you in class and just making modifications to it, you know, according to what's different about the homework problems. And so, you know, if you can, you know, understand the, you know, if you really take the time to understand these example codes and, you know, why I do, you know, certain, you know, why I do certain things the way I do, you know, it's going to help you tremendously for the MATLAB implementations. And so, so definitely use these as a resource. And so, you know, fully worked out examples like these are really nice, especially when you're coding, you know, because a lot, you know, I write these codes to be, you know, pretty flexible to work for many situations. Yeah. Yeah, so I'll let you guys talk about monitors. I actually don't have a monitor right now, so I'm actually just working on my laptop monitor. I have one in my office, but I obviously I'm not in my office right now. Okay. Right, and so that's for all the interior nodes, but we also have to implement our boundary conditions as well. Okay, and you can see, so you can see here the next 4 loops are, you know, for the boundary conditions. And so you can see that these have also moved inside of the time stepping loop. And so all our boundary conditions here are fairly simple in that they're just Dirichlet boundary conditions, right? And so we have a Dirichlet boundary condition of 50 on the left-hand side, a 50 on the top, a 25 on the right, and a 25 on the bottom, okay? And so, you know, we've seen this kind of a million times at this point. So, you know, I'm just going to kind of skip over that. And then we'll get to this part right here where we solve for the next solution, right? And remember, since we're doing an implicit Euler solution here, we have to do this with a, with a backslash, right? And so we say that the next solution is going to be A backslash B, and that solves our linear system of equations for that. And then from here, we always have to do this. And so after we solve for the next solution, we have to update the current solution. Okay. All right. And so from there, everything else is just basically, writing out, printing out the results and then making the video. And then don't forget this. And so remember, this is the most important thing. For things that change with time, you have to update the time variable. Okay. So don't forget that, because if you don't do that, then nothing in your solution is going to change with time. Right? Okay. I actually enlarged the font on my Matlab just so that you guys can, it's easier for me and for you guys to read. Okay. And so, I did make a couple changes, and so I changed that. So let's see how that changed our solution. I don't think it's going to change too much. Yeah, so you can see we still have our vibrating membrane. My laptop is begging for mercy, said, please, sir, don't make me do this anymore. So it's going really slow, but you can see that it's going. Okay. Right. And so if you run this code on your own machines, you should see that it produces an MP4 file called oscillating 2D flow. And so you can use that to view the solution afterwards. Okay. And so any questions on these examples here? Yeah, my laptop's been working hard recently. Yeah, it's but it's par for the course for these courses. Okay. All right, and so with that, you should be able to do all of homework 4 now. And so homework 4 is basically just on all of these time marching problems. And so again, use these sample codes, use them to your advantage, and just go ahead and modify the starter codes I gave you for that as well. Okay. So one last note that I'll make before we close this chapter in finite differences is that if you notice that, for both this example and the one we did earlier today, I used implicit Euler for these, right? And so that's not a coincidence. And so, whenever you have systems like this where, the boundary conditions, or more importantly, the convection velocities change with time, just what ends up happening is that you have it's much easier for the solution to go unstable, just because, because things are changing with time. It's likely that you might have one time step out of many where the solution goes unstable. And so usually for these kinds of problems, it's safer to go with an implicit Euler or some kind of implicit time marching scheme, just so that you don't have to worry about stability at all times. Okay. And so that's kind of why I made this decision here. And for your projects as well, it's you're going to use implicit Euler for that. Okay. Right. And actually, technically, by the end of this lecture right now, you should be able to you technically have everything that you need to do the project. And so, the project has, what you'll see is that it has two options. Well, if you're a grad student, you don't have an option. You have to do both. But if you're an undergraduate taking this class, you can either do the project with finite differences, which is what we've been doing up to this point, or you can do the project with finite volumes, which is going to be the subject, starting now, basically is going to take us up until the end of the class. Okay. Okay. And so with that, let me go ahead and bring back the laptop. Bring back my iPad. And then we'll start with just a brief introduction to finite volumes, which is our next big topic. Okay. And so this, now we're starting a new set of lecture notes. And so this is lecture notes 09, which, I had a feeling that we'd get to today. So I just uploaded those onto Canvas today. And so if you want to download it, you can go ahead and do that now. But this is basically introduction to the finite volume method. And so this is kind of a whole new method. And so, we're kind of closing the chapter on finite differences. So we've kind of done all we can with finite differences, minus one thing, which we'll cover later on. But the focus, from here on out is going to be mostly on finite volumes. Okay. All right. And so, the question probably, that's everyone's asking right now is, what is the finite volume method and how is it different from finite differences? Okay. And so before I kind of answer that question, let's kind of take a step back and think about, how, what we actually were doing with finite differences. Right? And so in finite differences, we basically work directly with the differential equations and we directly transform the derivatives into algebraic expressions, okay? And so if we had a situation that looked like this, is we had d squared phi dx squared plus d squared phi dy squared, okay, is equal to 0, right? And so by applying finite differences to this, we basically turn each of those derivatives directly into an algebraic expression, right? And so what we have is phi I plus 1, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j, all divided by delta x squared, okay, plus same thing for y, okay, divided by delta y squared, and then this gave us our our algebraic expression, right? And so, what we did was then we then took this and we solved this, for the solutions at the grid points or the nodes of our grid. And so let's say that we have our 2D domain, looks like this. Right? Okay. And then when we solve for the solution, we're solving for the solutions at these points that I'm, highlighting right now. Okay. And so the grid points were kind of our focus, right? Because that's kind of what allowed us to get our algebraic equation. Okay. All right. And so finite volumes, we're gonna approach this from a slightly different angle, right? And so the main difference in kind of how finite volumes gets its name is that instead of focusing on the grid points, what we're going to be focusing on instead are the cells. Okay? And so for finite volumes, I want you guys to look at a grid and not look at the points in the grid, but look at kind of the the empty spaces in between. Okay, so I'm just highlighting just random ones, and so there's nothing special about the ones that I highlighted, but it's just to kind of emphasize the fact that we're going to be focused more on the cells rather than the points. Okay, it's kind of like if you look at the FedEx symbol and you look at kind of the empty space between the the two words, and you see the arrow in that empty space, right? That's kind of what we're doing now. And so we're going to be looking at that empty space. I remember the first time my friend told me that, about the FedEx arrow in college, about, the empty space being an arrow. My mind was just like totally blown. I think it didn't help that my, I think it didn't help that I was a little bit less than sober during that time, but I remember that probably was one of my most life-changing experiences when I was in college. Probably more due to the drugs more than more than the FedEx arrow. Okay. All right. Any questions on this? Okay. All right. And so, that kind of gives you a little bit of a primer of what we're going to be, of what we're, what the finite volume method is. Okay. But, finite difference, finite volume, those aren't the only two, games out there, right? And so there's actually, a lot of methods that that are out there to for computational methods. Okay. In fact, there's so many computational methods out there. It's kind of way too many to cover in just one class. And so, for this particular class, and since the focus is mostly on heat transfer and fluids, I've chosen finite difference and finite volumes because those are the most common ones that you'll see for heat and fluids. But there's a lot out there. And generally, if you're kind of reading the scientific literature and you see a method starts with the word finite, that's usually a good indication that this is some kind of computational method, right? And so I would say I call these kind of the big three because these are kind of the three that are most commonly covered in at least in engineering curricula, right? And so we've done the first one already. And so the first one is finite differences. So most people actually start with finite differences because it's conceptually, it's kind of the easiest thing to conceptualize because you basically take your derivatives and you apply finite differences to them. Right? And so we call this FDM. Okay? The next most common is finite volume, which is obviously what we're going to cover next. And so this is called FVM. And a third one, and some of you are in this class too, is which is not this one, but it's 410, is the finite element method. Okay. Right. And so there's a lot out there, and different methods are, the end goal is the same. And so no matter what method that you end up choosing, the end goal is to take, a differential equation and turn it into an algebraic equation. And so the end goal is the same. And so, we're always going to end up with an algebraic equation because that's what a computer likes to do. Right? It's just the way that you get that algebraic equation is going to be different depending on the method that you choose. Okay. Yeah, my handwriting is not the best. Okay. And the question, and so probably the question you're asking is what which method is the best one or which one is used for what. And it turns out that each of these methods here, they have even though the end goal is the same and what they all do is the same, they each have their own kind of unique properties that make them good for certain kinds of situations. Okay. And so of course there's variations on this, like there's different codes out there that do different things. but I'll tell you kind of the general trends that these methods kind of go under. And so let's start with FEM. Okay. And so for finite elements, this is probably most commonly used for structural mechanics on complex geometries. Okay. And so the reason for that is because there's been a lot of research, you know, I think not too long ago, like maybe 20, 30 years ago, which basically was able to make a direct link between CAD files and you know, finite element simulations. And so basically they made it, basically, you know, the research made it super simple to go straight from CAD file to finite elements. And this really made finite element methods really take off for structural analysis. Because, you know, a lot of structural engineers, they're working with CAD anyway to develop their parts. And then, you know, through this method that the researcher developed, you can just jump right into a finite element simulation from that. Okay? And so if you've used SolidWorks, you know, you've probably seen, you know, SolidWorks simulation, or you might have heard of a software called ANSYS. Okay? Both of those work extremely well and extremely easily with CAD software. And so, you know, finite elements works really well for that. Finite elements also just works really well because it does really well with really complicated geometries, and, you know, discretizes it really, really well. And, you know, for structural mechanics, you're almost always going to be working with the complex geometry. Okay? And so FEM, I would say, is kind of the method of choice for more structural mechanics. On the other hand, FVM, which is finite volumes, this is I think the favorite method for CFD codes. And so a lot of the really powerful CFD codes out there are built on finite volumes. And so I think one that probably, you know, a lot of people are familiar with is OpenFOAM. And so I'm still trying to work so that, you know, we get to some OpenFOAM at the end of the class. Hopefully we'll have a week where we can learn that software a little bit. And so that's built on the finite volume method. You know, I know, you know, a lot of aerospace codes that like NASA uses, that, you know, they use the finite volume codes, the finite volume method as well. And so the reason for that is that the finite volume method actually very closely resembles probably a method that you've seen from your fluids class. And so if you remember from fluids, there's probably a method or a section in fluids where you did control volume analysis, right? And so you did control volumes with Reynolds transport theorem, and then you were able to analyze some fluid situations like that. And so the finite volume method actually closely resembles that, you know, very closely. And so finite volumes actually has a lot of really nice properties for fluid problems, in that, you know, mostly in that it's what's called mass conserving. And so you're basically guaranteed to satisfy conservation of mass for fluids in finite volumes, which is really important. And so finite volumes, you know, which is what we're going to go over, you know, is really, really good for those. Okay. Oh, sure. Yeah. So that's not a dumb question at all. So CFD stands for computational fluid dynamics. And so it's basically codes that are specifically designed for solving Navier-Stokes and solving for fluid flow situations. Yeah. Yep. Yeah. So finite volumes is used for that a lot. Right. And what about finite difference? And so finite difference, unfortunately, I can't say that I know any, you know, commercial or research codes that are built on finite difference. I have heard that finite difference is used often in like electromagnetics. And so that's kind of the code of choice for that, but I haven't actually seen any of those codes myself, so I can't actually confirm that. Finite difference, you know, I would say it works really well as kind of like an educational tool for kind of introducing people to the concept of computational codes. And that's kind of why I started with it in this class as well. Right? And so finite differences, even though, you know, for at least for my own work, I don't really see it that often. I think, you know, it's really nice and elegant in a lot of different ways. Okay. Any questions? Any questions on this? Okay. All right. And so let's go back and start. Let's go back and talk about finite volumes again, because that's kind of what we want to talk about. And so finite volume methods, remember, you know, what we're focusing on is not the points in our mesh, but we're going to be focused on the cells. Okay? Okay. And so let me give you examples of these in 1D and 2D, right? So in 1D, we have a line typically like this, right? And then we have grid points, let me just draw two just like this, okay? Normally, we're interested in these points right here, okay? But for finite volumes, what we're going to be interested in instead are going to be the spaces in between them, okay? And so instead of looking at this as, grid point 1, grid point 2, grid point 3, grid point 4, what we're going to look at them instead is we're going to look at them as cell 1, cell number 2, and cell number 3, okay? Where each of these cells are basically, defined in between the grid points. All right, and so now let's look at 2D. And so 2D, you've kind of already seen before. Let me draw our little chocolate bar here, okay? And so remember, instead of the grid points, what we're going to be doing instead is we're going to be looking at the cells. Okay? And so once again, instead of, grid point, how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Instead of looking at the 12 grid points, what we're going to be looking at are the 6 cells here. And so I really want to drive this home because I think it's kind of the hardest transition, when you're going from finite differences and you're looking at nodes. When you're doing finite volumes, it's about cells, okay? And so I'm going to use the word cell to kind of, to reference, both of these kind of things, right? And so, I know the method's called finite volume, but then, obviously in 3D, if you have a 3D cell, it's called a volume. We can have cells in 1D and 2D too. And so that's why I use the term cell for that. But I guess, finite cell method never caught on. And so I guess finite volume was a more, more attractive name than finite cell method. Okay. All right. And so what is this, mathematically, what does this allow us to do, right? And because now that we're looking at the cells more than the points, these cells occupy a finite region in space, right? And that's what I've kind of highlighted in light blue right there, right? And, now that our cells, now that our focus is on these cells and, these cells occupy a finite region of space, this opens up a new mathematical tool to us. Well, it's not new, you've known it for years now, and that's integration. Okay? Because whenever you have, a region of space, you can always integrate on that, right? And so if you take kind of this 1D case, we can just basically perform an integral. And so we'll call this x2 plus x1 and x3, right? And so to integrate over the space, we can just basically take the integral from x2 to x3, right? And then, we can put whatever we want inside here, right? And so, by integrating or by, looking at the cells, integration becomes available to us now. And that opens up a whole new world of mathematical possibilities, right? And in some sense, it kind of seems like we're going backwards because it's, I remember because, for these methods, we want an algebraic expression, right? But, by performing integration, it kind of seems like we're getting farther away from algebra because, we're going much more into calculus. But what you'll see is that, by performing integrals, what we can do is we can apply, integration rules and kind of simplify our equations a little bit to get a different, so that we can come to our algebraic equations in a slightly different way. All right, question. So I was writing out this equation and you mentioned nodes again. So we're focusing on the cells, but the cells are defined by nodes still. Yes. And so we'll still have nodes in our grid because, we need those to define our cells. It's just that, now we're going to be focused instead of finding solutions at the node points, we're going to find the solutions inside of our cells. Yeah. So you'll see more on that next week, but we're just about out of time. But basically, what we're going to do is we're going to take our governing equations perform an integral over these to integrate over them over a cell, and then use that along with some integral transformations in order to get our algebraic equations from there. All right, question. So are the nodes still used as BC? So they won't be. And so actually now, well, in 1D, they will be. And so in 1D, you know, we just have nodes there. And so the nodes will be a boundary condition there. But for 2D, you know, we're instead going to be applying boundary conditions on these edges instead. And so our boundary condition, you know, it's going to be a little bit different than it was before, you know, with the finite volumes. But, you know, we'll walk through it kind of step by step this whole time. Question, so will we still use arrays to hold the values? Yes. And so instead of having an array of nodal values, what we're going to have instead is an array of cell values instead. Yeah. All right, and so we're just about out of time. And so let me wrap it up here for this week, and then we'll continue this discussion next week. So it's a little bit of a cliffhanger, I know, but what we'll see next week is that, you know, with this integration, you know, we'll be able to come to our algebraic equations in a different way. All right, so thank you guys for tuning in as usual. I hope you guys enjoyed today's lecture. Have a great weekend. Stay safe, and I'll see you next week.
Thank you, Professor.
Thanks, guys.
Professor, could you go back to the first page of the notes, please?
Yes.
Thank you.
Yep.
All right, Daniel, did you have any more questions?